Hello students, welcome back to Math 332 Linear Algebra. In this video, we are going to talk about the concept of diagonalizations. So in the previous video, we learned what is eigenvectors and what is an eigenvalue. And today, we're going to get an opportunity to see how it is used to help diagonalize the matrix. And in the future videos, in the next videos, we are going to look at why the diagonalization process is important. And we're going to show you two examples that diagonalizations can help us solve a system of differential equations, and it can also help us solve something called the difference equations. Actually, it can help us solve a lot of other problems, but in this course, we're just going to show you these two examples. All right, without further delay, let's get right to the concept of diagonalizations. All right, let's first look at the objective for this sections. So at the end of this video, the key thing is that you need to know what does it means for n by n matrix to be diagonalizable. And you also need to know the criteria for such n by n matrix to be diagonalizable. Okay, so why do we need to diagonalize a matrix? Well, let's start by looking at this matrix. This is a 2 by 2 matrix. Okay, so if I ask you to compute what is a square, you will have to do this. And if we ask to compute a cube, you have to multiply these three matrices together. All right. And if you multiply all these matrices together, you will see that in general, okay, if I ask you to compute a to the power of n, this is definitely not 1 to the power of n, 2 to the power of n, 3 to the power of n, 4 to the power of n. It is not. So because of that, the computations like this is going to be pretty tedious because there's no general pattern for it. However, if you look at a diagonal matrix, such as this one, if you compute d squared, you will see that d squared is actually this. And if you compute d cubed, then you will see that d cubed is actually this. So in general, you can show that d to the power of n is nothing but 1 over 2 to the power of n, 0, 0, 1 to the power of n. And this is one very important feature for a diagonal matrix, which is that d to the power of n is nothing but, okay, if your matrix is diagonal matrix, then d to the power of n is nothing but this, okay, which is every entries in the diagonal will raise to the power of n. So we have a general pattern for the power of a matrix if the matrix is a diagonal matrix. All right, so now let's look at another type of matrix. So this time we have a matrix B, which is written as the product of these three matrices, and assume that the matrix P is invertible. So we can write B as the product of P, multiply this diagonal matrix, and P inverse. So what is B squared? All right. Okay, so if we call this matrix D, then B squared is going to be P D P inverse, right? Multiply P D P inverse. Now, because matrix multiplication is associative, so we can write like this, and P inverse and P will make an identity matrix. So you have something that looks like this. All right, so here this will be P D squared P inverse. So actually, we can kind of see that if this is B squared, then it will be PD squared P inverse. And D is a diagonal matrix, so we actually know very well how to do that computations D squared. And actually, you can show that, okay, you can show that we have the following. All right, so B cubed is going to be like this, B to the power of 4 is going to be like this, and in general, B to the power of n is going to be like this. So this is also a pretty nice matrix. And again, we know that this dn is computed by simply raising the diagonal entries to the power of n. All right, so after all this example, we are now ready to talk about the definitions of a matrix A being diagonalizable. All right, the definitions is this. A n by n square matrix, right, is diagonalizable if you can find a diagonal matrix such that P inverse AP equals to D. So obviously, a matrix A is diagonalizable. It doesn't mean that you can write equals to a diagonal matrix, because you can't change a non-diagonal matrix and make it equal to a diagonal matrix. So when we say a matrix is diagonalizable, we means that A, sometimes you see people write notation like this, A is diagonalizable, is equivalent to a diagonal matrix, which means A is diagonalizable if and only if there exists a invertible matrix P such that P inverse AP equals to D. So that's the definitions for a matrix, a square matrix, to be diagonalizable. All right, so now that you know the meaning of a matrix A being diagonalizable, the next obvious questions is what are the conditions so that A has to satisfy so that A is diagonalizable, okay? So what are the conditions, what are criteria, what are things needed to make a diagonalizable matrix? And the answer is pretty nice. It's given by this theorem, which says that A is diagonalizable if and only if A has n linearly independent eigenvectors. All right, so the key thing for a matrix to be diagonalizable is that the matrix A has to have n linearly independent eigenvectors. So now you see the questions of diagonalizable of a matrix is closely related to the eigenvalue and eigenvectors problems that we saw earlier. Okay, and in fact, this is a very nice theorem in the sense that it's a two-way theorem that says that A is diagonalizable, then the matrix A must have n linearly independent eigenvectors, and if A has n linearly independent eigenvectors, then the matrix A is diagonalizable. And the proof is also very nice. The proof is what we call a constructive proof, because while looking at the proof, you know exactly how to construct the matrix P such that P inverse AP equals to D. Sometimes you have a theorem where the proof is not constructive, especially in a lot of cases when we talk about, say, for example, existence of a solution of a differential equation, for example. They can tell you that on that particular regions, the solution for the differential equation exists, but the proof didn't tell you how to find that solution. So those are non-constructive proofs. So in mathematics, we sometimes have like non-constructive proof, but when we have constructive proof, the proof actually show you how to find something. So in this case, you will see that you go through the proof, you will see that how we actually construct a matrix P so that P inverse AP will equal to a diagonal matrix. All right, let's look at the, since this theorem is a two-direction theorem, let's look at the proof and look at the easier direction. So the easier direction will be this. So suppose A is diagonalizable and we want to show that A has n linearly independent eigenvectors. All right, so let's see how we're going to do that. Okay, so remember our hypothesis now is that A is diagonalizable. Okay, so if A is diagonalizable, we want to show A has n linearly independent eigenvector. All right, so this is what we're going to do right now. So remember, hypothesis is that A is diagonalizable. What does it mean? What does it mean that A is diagonalizable? Well, according to the definitions, it means that we can find a matrix P, and not just any matrix. It's just an invertible matrix, okay, matrix that has inverse, and also a diagonal matrix D such that P inverse AP equals to D. So we have a D that looks like this, we have a P that looks like this, okay, and we want to show that actually you will see in a minute that all this P are actually eigenvectors. So let's see why this is true, okay? So we know that we have P inverse AP equals to D. So this is the P. It is invertible by hypothesis because A is diagonalizable, means that there is such invertible matrix. So we know this matrix is invertible. And so if P inverse AP equals to D, so if P inverse AP equals to D, then AP will equals to PD, okay? So let's compute what is AP and let's compute what is PD and equate them and see what we get. All right, so what is AP? So from the very beginning of the semesters, we know that matrix multiplication have some special property that you need to be aware of. One of the properties that we mentioned is that if you write your P, matrix P like this, which is individual column, then if you multiply AP, that is the same as A multiply P1, okay, P1 is this column, and then put it right here in the first column. P2 is this column, and AP, you multiply this. The second column of that matrix product AP is going to be AP2. The last column for that product AP is going to be APN. So this is what happened when you multiply A and P together, okay? All right, so now we have AP. Let's compute what is PD. Okay, so this is going to be your PD. All right, this is going to be our PD. So P is this column vector, P1, P2, all the way to Pn. D is this diagonal matrix. Now, if you, again, pay attention to what we learned in the first week of class regarding the matrix multiplications, you can see, for example, if you concentrate right here,
if you are looking at this one right here, multiply this matrix. So we are doing something on the column of this matrix, and in particular, in this case, we are taking lambda 1, multiply this, and then 0, multiply this, and then 0, multiply all this, all the way to 0, multiply this. So the first column here, what you get is lambda 1 p1. Okay, remember that a long time ago when we talked about this matrix multiply this matrix, okay, what happened for our first column is going to be lambda 1 multiply this plus 0 multiply this plus 0 multiply this, at the end plus 0 multiply this. So obviously what you get for PD at least in the first column is lambda 1 p1. So same thing applies to this, okay, so same thing applies to this. You get lambda 2 p2, so on and so forth. So in fact your PD right here, okay, will looks like this. Okay, so the PD will looks like this. All right, so now that you have AP looks like this, PD looks like this, so if you equate them, if you equal these two matrices together, you will see that your AP1 will equal to lambda 1 p1. Your AP2 will have to equal to lambda 2 p2, all the way to like APN will have to equal to lambda n pn. So now you see that AP equals to PD give you this. And what is this? So you have a vectors p1 multiply AP1 and you get lambda 1 p1. That means that the p1 here is actually an eigenvectors for this matrix A with corresponding eigenvalue lambda 1. See that? And P2 here is actually an eigenvectors for matrix A with corresponding eigenvalue lambda 2. So in fact, what we have shown is that if A is diagonalizable, all right, diagonalizable, right, then we will have P, okay, P1, P2, we have, and, okay, linearly independent eigenvectors, okay, linearly independent eigenvectors, right? So we have n of them. All right, so we actually found n eigenvectors, but how do you know they are linearly dependent? All right, from this computation, actually, we have shown that we managed to find, okay, n eigenvectors. Okay, if A is diagonalizable, you can see we found n eigenvectors. But how do you know they're all linearly independent? Well, it's because, okay, this is because your matrix P that is constructed like this is invertible. Think about it. If your matrix P, which is constructed like this, is invertible, then, okay, all the column vectors here has to be independent. They all have to be linearly independent, okay? I hope you can see why. So because P is invertible, so we found n eigenvectors, and they must be all this eigenvector here must be all linearly independent. So this is the first part of the proof. All right, so we have seen this part of the proof, okay? That is, if A is diagonalizable, then A has n linearly independent eigenvectors. Now, the other direction is actually more helpful, which is if A has n linearly independent eigenvectors, all right, then A is diagonalizable. So how is it, like, if you have n linearly independent eigenvectors, how do you make A diagonalizable? And the way we do it, okay, is going to be this. All right, so suppose, okay, from the hypothesis, we have all these eigenvectors. So being eigenvectors has this property, and we're going to place all the eigenvectors inside this matrix P as the columns of matrix P. All right, so this will give us P, n by n matrix. Now, again, because all this P are not just any vectors, but they are independent. They are linearly independent vectors. So this matrix P constructed this way has to be invertible. Again, think about why, okay? Make sure you know why. But if all this column vectors, okay, all these column vectors here is linearly independent, and you place it inside this matrix P like this, then the matrix P has to be invertible. All right, so now if you do these computations, okay, AP, so again, AP is going to be A, there's a typo here, A times P, which is like what we said, we have all this AP1, AP2, all the way to APN, but now those P are actually eigenvectors, so this is going to give you lambda 1 P1, lambda 2 P2, all the way to lambda n Pn. And again, you can see this is actually the product of these two matrices. And so we have AP equals to PD. And P, because all these column vectors are linearly independent, so all this matrix means matrix P is invertible. So multiply the inverse on both sides. So you get something that's like this. This cancel out, give you the identity matrix, and this is going to give you D. And now we have P inverse AP equals to D. And what is D, by the way? D is this matrix. It's a diagonal matrix. So now you know that by placing the eigenvectors, as the columns of this matrix P, as a column of this matrix P will give you P inverse AP equals to D. And by definitions, that means that A is invertible. All right, A invertible by definition. Had to say invertible? No, I mean A diagonalizable. A diagonalizable by definitions. All right, A diagonalizable by definitions. All right, let's look at this particular example. Okay, so you have a matrix A, and we can show that this P1 here is an eigenvector, correspond to this eigenvalue, and P2 here is an eigenvector, corresponds to this eigenvalue. Okay, and now if you place your P, if you construct your P, so make a P. All right, so if you put P1 here and P2 here, all right, so if you make P1 and P2, okay, can you see it? So if we make our P1 here as the first column of this matrix, P2 here as the second column of this matrix, then they are invertible. Why is that so? Because P1 and P2 here is actually linearly independent. We can check that. And if you do it like that, P is invertible and P inverse AP will equal to the D. And what is D? D is the eigenvalue corresponding to this particular eigenvector. All right. Okay. And 7 is going to be the eigenvalue corresponding to this particular eigenvectors. Okay. Now, from the proof, from the constructions, we actually know if you set this differently, or if you put P2 instead of P1, if you put P2 as your first column and P1 as your second column, so look at this, right? So P2, you put it here first, and then this is P1. If you do it like that, P inverse AP will give you a D, but the D will be different. The diagonal matrix will be the 7, -4 instead of -4, 7. The reason is we are supposed to get the eigenvalue corresponds to this eigenvector here. Okay, this positions should be an eigenvalue corresponds to this eigenvector here. So as you can see, if you place the column vectors differently, if the column vectors consist of the order of the eigenvectors inside this P is different, then you will get different diagonal matrix. But it doesn't really matter. The matrix A is still diagonalizable, because A is diagonalizable simply means that you can find a matrix P such that P inverse AP equals to a diagonal matrix, not the diagonal matrix. So a diagonal matrix. So it doesn't doesn't really matter so much that which one is the diagonal matrix. So the diagonal matrix could be this, or it could be this. It doesn't really matter. All right. All right. What do we know so far? So we know that. Okay, so we know if A is n by n matrix. Okay, so what we know so far is this. A is diagonalizable if there exists an invertible matrix P and a diagonal matrix D such that P inverse AP equals to D. That's the definition. And we also know from a theorem that says that if A is diagonalizable if and only if A has n linearly independent eigenvectors. All right, again, so our matrix A is a square matrix n by n. All right, so A is diagonalizable if and only if A has n linearly independent eigenvectors. So the question now is, how can we guarantee that a matrix A of size n by n can actually have n linearly independent eigenvectors? Number one, does it always happen that way? Number two, how can we tell whether we can have enough eigenvectors, enough linearly independent eigenvectors, right? So that question is completely answered by this theorem. Okay, the theorem says that a matrix A, n by n, all right, okay, is diagonalizable, okay, if and only if the geometric multiplicity of every eigenvalue is equals to the algebraic multiplicity. Now you know why we talk about the algebraic multiplicity and geometric multiplicity from before, okay? So you will see in a minute that this is actually not rocket science. It's actually pretty easy to see that matrix A is diagonalizable if and only if the geometric multiplicity for the eigenvalue, for every eigenvalue, has to equals to the algebraic multiplicity. If you have that, then we will definitely have guarantee and linearly independent eigenvectors. So therefore, we can diagonalize the matrix. Okay, so the geometric multiplicity and the algebraic multiplicity is basically a measures. Okay, it basically a measure to tell you that whether we can have enough linearly independent eigenvectors or not. Okay. All right, let's look at it with an example. So let's say you have a matrix A. If you compute the characteristic equations for this particular matrix, okay, that is to compute the determinant of A minus lambda I and set it equal to 0. All right, suppose you have this as a characteristic equation. Now we know lambda equals to -1, okay, is an eigenvalue. Lambda equals to -1 is again another eigenvalue. This is what we call basically, you can write this as lambda plus 1 square, right? So one of the factors is lambda plus 1 square. So we say that because of this repetition, we say that lambda equals to -1 has algebraic multiplicity 2. Have algebraic, okay? That's algebraic multiplicity 2. And lambda equal to 2 right here because it's this factor appear only one time. So we will say that lambda equal to 2 have algebraic multiplicity 1. Now, because A is a 3 by 3 matrix, so we better make sure that we can have 3 linearly independent eigenvectors. If we can find 3 linearly independent eigenvectors, then the matrix A will be diagonalizable. Now, we know, okay, so we know from experience from the previous video that this lambda equal to 2 will give you an eigenvectors. Let's call it V2. It should be okay. Let's just call it V. All right. Now, this is a problematic spot. This one here, because your lambda equals to -1 appeared twice, okay? So if you compute the eigenspace, okay, which is a basis, right? If you try to find all the linearly independent eigenvector for this particular eigenvalue, that is a possibility that we can only find one, okay, linearly independent eigenvectors for the eigenspace. If that is the case, then we're going to be in trouble because in total, we are going to only have 2 linearly independent eigenvectors for a 3 by 3 matrix. This is not enough. So this is a problem here. But for algebraic multiplicity 2, if you compute the eigenvectors for that particular eigenvalue, lambda equal to -1, the eigenspace maybe have a basis that has 2 vectors. So let's say U and W. So if you have that, okay, that is to say that the eigenspace has 2 linearly independent eigenvector. I'm saying the basis, right? The basis for the eigenspace, if you can have 2 vectors, linearly independent eigenvectors to make up the basis for this eigenspace, okay, for this eigenspace E -1, then altogether you have 1, 2, right, and 3 linearly independent eigenvectors. That will be enough, okay, in this case, to diagonalize this 3 by 3 matrix. So the question now is, okay, when you compute the eigenspace for this eigenvalue, okay, is the basis for this eigenspace consists of 2 linearly independent eigenvectors or just 1? Okay, so let's do that computation now. So if you do the computations, this is something that we have from before, you will see that your E -1, which is the eigenspace for this eigenvalue, lambda equals to -1, and you will see that we managed to find 2 linearly independent eigenvectors to make up the basis for this eigenspace. So the geometric multiplicity for this eigenvalue is 2. All right, so this geometric multiplicity for this eigenvalue is 2, and the algebraic multiplicity is also 2. So you see that the algebraic multiplicity is 2, the geometric multiplicity is also 2, so it matches. So for this lambda equals to -1, the algebraic multiplicity and their geometric multiplicity is the same. All right, so if you look at this eigenspace, lambda equals to 2, which is for this, right? For this eigenspace, lambda equals to 2, you can see that one of the bases that we can get for this eigenspace, so this is the basis. So one of the bases we can get for this eigenspace is this vectors. So we can take 1, 1, 1 as a basis vector for this eigenspace. So what does it mean? It means that in this case, the algebraic multiplicity for that lambda equal to 2 is 1, and so is its geometric multiplicity. So in this case, you can see that the algebraic multiplicity and the geometric multiplicity also matches. So we have matrix A diagonalizable by this theorem, because this theorem says that if it is 3 by 3, okay, if it's a square matrix, if the eigenvalue, all the eigenvalues, their geometric multiplicity and their algebraic multiplicity matches, then they are diagonalizable. And why is that so? Because the geometric multiplicity is there to make sure that if your algebraic multiplicity is 2, I should be able to find 2 linearly independent eigenvectors to match it. Otherwise, if I have less than that, then I'm in trouble. Okay, so let's summarize this. So in this case right here, we have algebraic multiplicity 2, geometric multiplicity 2. So lambda equal to -1, have all these 2 quantity matches. And lambda equal to 2, we have algebraic multiplicity 1, geometric multiplicity is also 1. So in this case, we know that matrix A is diagonalizable. In fact, if you compute the eigenvectors, so this is the eigenvectors for lambda equals to -1, and this is the eigenvectors for lambda equals to 2. So if you arrange it this way, P inverse AP is going to give you this diagonal matrix, all right? Remember that this matrix, this particular column vectors is an eigenvectors. This is the corresponding eigenvalue. Oh, sorry. Okay, if this is the eigenvectors, all right, this is the corresponding eigenvalue. This is the eigenvectors. If you place it like that, this is the corresponding eigenvalue. This is the eigenvectors. So if you place it like that, this is the corresponding eigenvalue. So now we see that A is invertible. Keep saying that. A is diagonalizable. Diagonalizable. Now, let's look at this particular example here. So now A is 4 by 4 matrix. Okay. And let's compute the determinant of A minus lambda I and set it equal to 0. Now this is easy because this is actually an upper triangular matrix, so we know how to compute the determinants very easily. Just take the products of the diagonal entries. So in this case, immediately you will see that the characteristic equations will be like this, okay? Lambda minus 2 raised to the power of 3, lambda minus 4 raised to the power of 1 equal to 0. So immediately, we know the algebraic multiplicity is 3 for this eigenvalue lambda equal to 2. So algebraic multiplicity is 3. Okay, so lambda equal to 4 will have algebraic multiplicity 1. All right, so that's very easy to see. Now, in order to compute the geometric multiplicity, I'm being lazy here, so I'm just use GM to do that, and GM, right? In order to compute the geometric multiplicity, you will have to compute the eigenspace, right? So you have to compute the eigenspace. So in this case, the eigenspace for the lambda equals to 2 is very bad because it is actually just spanned by one vector like this. So the basis, all right, for this eigenspace is actually just this. So the basis is just this, right? So the geometric multiplicity is defined as the dimensions of the eigenspace. So the dimension is the number of vectors. So the number of vectors for the eigenspace. So it is 1. Okay. So now you see the algebraic multiplicity and geometric multiplicity does not match, right? So here we are hoping that they can give us 3 independent eigenvector, but we only have 1. Let's call it V. Okay, which is in this case 1, 0, 0, 0. Now here, if you compute the algebraic multiplicity for lambda equals to 4, you will see that you can get 1 independent eigenvector from V. Actually, obviously, right? If you have, you definitely will have at least 1 independent eigenvector. So this case here, we'll have another U. Okay, you can compute that and figure out what that thing is. But the geometric multiplicity here will be 1. And you will see that that's not enough. We have 2 linearly independent eigenvectors. This is a 4 by 4 matrix. So we're supposed to have 4 linearly independent eigenvectors to diagonalize that matrix, but we don't have enough. And the reason that we don't have enough is when you have algebraic multiplicity like this, your geometric multiplicity is actually always less than or equals to algebraic multiplicity. So actually what happens is that your geometric multiplicity is bounded above by this number here. So when you have algebraic multiplicity 3, then your geometric multiplicity is either 1, 2, or 3. So if you don't hit 3, if you have either 1 or 2, then you're in trouble because you cannot extract enough linearly independent eigenvectors for this eigenvalue. So in that case, they are not diagonalizable. The matrix A is not diagonalizable. Okay? All right. So what have we learned so far? So what we have learned so far is the definition of diagonalizable. Okay, a matrix being diagonalizable. We have a criteria to determine whether a matrix is diagonalizable. It all depends on do we have enough linearly independent eigenvectors, and that is actually also what this theorem is saying. So I hope you follow what's going on, and now let's look at some questions. Okay, let's look at some questions. All right, question number 1. If your A is a 3 by 3 matrix and you have all this as your eigenvalue, okay, these are all the eigenvalue, and suppose we know that UV is a basis for this eigenspace E1 and W is a basis for this eigenspace E2. Questions, okay, questions. Is the matrix A diagonalizable? And if it's diagonalizable, if you take a P like this, what is the matrix D? So first question. Second questions. Suppose your A is a 4 by 4 matrix, and these are the eigenvalue. Okay, these are the roots of the polynomial. That means that's an eigenvalue. Okay, just another way of saying it. And suppose U is a basis for this eigenspace E1, V is a basis for this eigenspace E2, and W is a basis. Okay, the sets W is a basis for this eigenspace E3. Questions: is matrix A diagonalizable? All right.
All right, I will give you a moment to think about the problems, and you can pause the video, and when you are ready, you can restart the video, and I will be here and show you what I got. See you very soon.
All right, welcome back. All right, let's look at the solutions. Okay, so we have lambda equals to 1, okay, and lambda equals to 2. All right, lambda equal to 1 appear twice. Okay, so counting multiplicity, you know that the algebraic multiplicity for lambda equals to 1 is 2 because you will have a factor like that in your characteristic polynomial because you have 1 comma 1 as the roots, right? Makes sense? All right, so the algebraic multiplicity for lambda equal to 2 is 1 because it appears only one time. In the factor form, you get to see that this thing here has a factor 1, this thing here has a factor 2. Your characteristic polynomial will be something that looks like this. All right, so the matrix is diagonalizable or not, okay? We'll have to make sure that geometric multiplicity for this one have to be 2 if it is diagonalizable. Do we have that? Well, the question tells you that UV, the set of UV, is a basis. It's a basis for this eigenspace. All right, so geometric multiplicity is defined as the dimensions of that basis, of that eigenspace, which is the number of vector in the basis. Right, geometric multiplicity for this eigenspace is defined as the dimension, right? Geometric multiplicity for the eigenspace is defined as the dimensions of that vector space, and the dimension of that vector space is the number of vector in the basis. So, dude, this is telling you that this is 2. All right, so this is telling you that this is 2. So what do we know? We know that we have enough eigenvectors, okay? We have enough eigenvectors for this eigenvalue lambda equal to 2. So here you will have geometric multiplicity equals to 1. Why? Because this is the basis for this eigenspace, okay? So now we have algebraic multiplicity and geometric multiplicity matches. Algebraic multiplicity and geometric multiplicity for this lambda equal to 1 matches. So all the eigenvalue, their algebraic multiplicity and their geometric multiplicity matches. So by theorem, they are diagonalizable. A is diagonalizable. And in fact, we have enough eigenvectors, enough linearly independent eigenvectors to diagonalize the matrix. So if you place your P, so this U, V, and W, they're all linearly independent, all right? So U, V, and W, they're all linearly independent. So if you put it into your matrix P like this, your matrix P is invertible, and P inverse AP will give you a diagonal matrix, okay, where the entries here, right here, is the eigenvalue corresponds to this eigenvector. So U is the eigenvectors for lambda equal to 1, so you have a 1 here. W is an eigenvectors for lambda equals to 2, so you have a 2 here. And V is an eigenvectors corresponds to eigenvalue lambda equal to 1, so you have it here. So your matrix A is diagonalizable, and your D is this matrix, okay? If your P is chosen like this. All right, straightforward. Okay, so the solutions for the second problem here is, all right, let's do the same analysis. Lambda equals to 1, okay, 1, right? Okay, so algebraic multiplicity, right, for lambda equal to 1 is 2. Lambda equal to 2, okay, algebraic multiplicity is 1. Lambda equals to 3, the algebraic multiplicity is 1, okay? Because this is 4 by 4 matrix, these are the roots of that polynomial. So you know that we definitely have a factor that's like this, we definitely have a factor that's like this, and we definitely have a factor that's like this. All right, equals to 0. All right, so now with that in mind, let's look at the geometric multiplicity. All right, is it 2? Is it 2? All right, so U is a basis for this eigenspace E1, right? Which means that the dimension for the eigenspace is 1, so the geometric multiplicity is 1. So now you know, oops, I don't even have to care about the other stuff, okay? Oops, okay? The algebraic multiplicity and geometric multiplicity does not match. Therefore, A is not diagonalizable, okay? A is not diagonalizable.
Very well. So this concludes our discussion on diagonalization process. And the next video, we are going to see how we can apply this diagonalization process to solve a system of differential equations. And also we're going to see how we can use it to solve what we call difference equations. All right, we'll see you in the next video very soon.